So did anybody do their homework? Which one? The ducks. Okay, turning the ducks into GMPEs and understanding what those different things look like now. You did your great. Well, we're going to try to go through this a little bit more of understanding what this visualization is all about. One way, so we're waiting for Steve, so I'm going to stall a little bit. We need to develop weights for these different models. And in developing the weights, it's traditionally been a subjective process as well in terms of relative merits of models, but we want to be able to check how different are the models. Is one really just a very small change from a neighboring model? And that's what this kind of a presentation lets you do. It lets you organize those models and try to get an objective evaluation of how to weight them and still capture the right space. Here comes Steve. So, Nico,
yes, I'm coming.
You're ready to go.
All right, good afternoon, everybody. So we're going to continue from yesterday by showing the results. Today is actually the more complicated part than yesterday. So yesterday was just the technical basis, but now that we have the results, we need to think about what we want to do with this. And I think this is a bit more complicated, and I don't really have a solution to that. But this is just the same slide as yesterday, what we're going to do. Trying to answer the question how similar are different GMPEs by mapping them from a high-dimensional space to a low-dimensional space. Yesterday we talked about how we do this. So this is what it looks like. Same slide as yesterday. We have here the average of all the models. And then we have in this direction like up and down scaling. We have in this direction differences in magnitude scaling, like shown here. And then we have in some other direction differences in distance scaling. And then what we can do is we plot all the GMPEs on top of that. And then most of them are in this range, so they're actually covering broadly this range made up of the extreme scaled reference model, except the Bindi et al. Model from 2011, which has this weird distance scaling I'm going to show you. So what this plot can, or what we can't do here is like automatically set weights. But what we can do is say which models are similar, what weights do we need to give to end up in some place. And also, is this mixture model, then is it well covered? Then we have, that means we have models which differ from there in like up and down scaling. We have models that differ in magnitude scaling and so on. Probably would be a bad idea if we had some directions where we don't have any model at all. The thing is, we still need to think about where we want to end up in the end. So basically, I think depending on the weights you give, you could end up anywhere between these models. But this doesn't really tell you where you want to end up. So this is what you need to know beforehand, I think. But it can tell you if you can end up there by using all the models that we have. So this is the one for PGA. We see most of the models quite well concentrated. This is the same thing using self-organizing map. Just a reminder, so dark colors are large distances between neighboring nodes, and lighter colors are small distances between neighboring nodes. We have here the mixture model. And then, because this is a nonlinear representation, we don't really have like really a straight line between the extreme scaled models, in particular for the magnitudes here, but we still have, at least for PGA, some general directions. And if we then take the smallest distance between all the models, plot them onto a map, it looks like this. Here again, I don't really remember what the colors are, so what the symbols for the reference models are. So triangles are scaling up and down. Squares are distance scaling, and then I think this is pretty similar to the Simmons map that I showed on the plot before. So again, most of the models are concentrated around their average, and there's just one model which is far away. So this is the reason why it's far away. There's this really weird, unconventional distance scaling above a magnitude 6.5 for PGA, which is just because they don't have any data there, and which just tells us, okay, we shouldn't really extrapolate beyond this point. What we see down here, this is the residuals between the mixture, or the average of all models, and the Bindi model. This is against magnitude and against distance, and the color code is, in this case, by distance. So that means same colors mean same residuals for the same distance. Residuals for the same distance. And bluish colors are small distances, and then reddish colors are large distances. The same here, bluish colors are small magnitudes, and reddish colors are large magnitudes. Just going through this for all the periods. So again, we have periods PGA 0.2 seconds, 1 second, and 3 seconds. This is what it looks like for 3 seconds. Again, we have here our extreme scaling models. Now the Bindi et al. Model moves a little bit closer to everything else, to the other models. But when you look at that, it seems like the other models take a little bit more space. This is how it looks like, but still they cover, or they surround their average like in all directions. Yes, sure.
Before you go on, looking at this right now, you've got the Campbell and Besorgnia 13 and the Grazer and Calcon 13 are actually closer together, right? To the left.
Yes.
Up
These
those
ones,
two,
yes.
right? Even though those
Right.
are really different, fundamentally different data sets
Yes.
and approaches.
Yeah.
So this is similar in the magnitude and distance scaling over what magnitude range and what
So this
distance
is again.
range?
So this is all 5 to 8,
5 to 8.
and then distances from 1 to 200 kilometers.
Okay.
And everything in this case. So all these points are weighted equally.
So we could do this though, saying I want to be 0 to 15, for
Yes.
example, and just
Yeah,
focus
yes,
it on that.
right.
Because that might change this, the way this
It will.
map looks.
It will. It definitely will. So this is again this self-organizing map. We see again. So the mixture model is always in the middle. We still have down here should be the Bindi model, which is still a little bit far away. And one of the nice things, we have, is that there's not really any like big boundary. So there's nothing going on like this, which with darkish colors, which would mean that we have some models which are really different and which are really separated from everything else. So
Nico, what's in the corner? That's the blue, the lower left.
this one,
Yeah.
this should be the Bindi model.
Okay.
And here, this is the R model, which is, let me see, which is this one.
Steeper.
Yes. Okay. The same thing for 1 second. In general, so what we see is that the Grazer and Calcon model actually moves out a little bit for longer periods. overall. This will, I think, it's even more pronounced for 3 seconds, whereas
But I'm still trying to keep
Yes.
track of all this. It's moving out in that direction that looks like a magnitude scaling direction. Is that
yes, so
still a
this will
valid?
be something like a magnitude and
distance, because they're
scaling.
both-
So it's like in between. It is really difficult. Well, the problem is if you move in one direction, everything changes, of course, because you can't really say if I go there, then only one thing changes.
So minus minus is a flatter curve.
Yes,
Or-
minus minus would be this curve.
Okay. And plus plus is a
Plus is the
steeper magnitude
steeper
scaling.
magnitude scale.
And the same on the distance, is that right?
No, the distance you have minus minus is
Is
actually
steeper.
steeper one, and yeah, I should change that. Okay. This is basically what the model looks like. So now we have the Greiser and Kalka model being pushed to the edges and being quite far away from everything. Bindi model is still quite far away, and well, you can't really like say this is like compare the distances because this is just far away from everything. But it's just it's between these two extremes here. So it's between the m plus, it's a different magnitude scaling and a different up and down scaling. And we see that in general, all models are a bit farther away now at 1 second. And this is the same thing for 3 seconds. So now, again, we see the Greiser and Kalka again moving out of the other ones, whereas the Bindi model is still far away, but it's not as far away as for PGA.
I thought Bindi stopped at 2 seconds. Is it 4 seconds?
4. Is that 2? No. I think they at 2. Okay, then we should discard this data point there. And again, you see here we have the Greiser and Kalkan. So again, remember this is a nonlinear, like a nonlinear 2D representation, whereas the other ones are a more linear 2D representation. But again, we see we have different directions. The problem is now, since it's nonlinear, they don't align on this in a direct line anymore, but we can still appreciate the spread of all the models and where we might have actually problems with models.
How do we, when something's near the middle, excuse me,
Yes.
what interpretation should we be making of a model that's more in the
If
center?
something is near the middle, then it's near the average of all the other models.
Because was the mixture model defined to be in the middle?
Yes. Well, the mixture model, so this is all models equally weighted.
So by definition.
By
it's-
definition, it is like the average of all models.
So I would say here, Campbell and Besorgnia 13 is close
close,
to
right.
the average model for t equals 3 seconds.
Right. The same for the Idris
Idris
model.
model, okay.
Okay.
So
But-
if we were looking at creating a model, let's say we decided we don't have enough space or
right.
have expanded. We're adding the epistemic uncertainties that Bob and Linda have been
Yeah.
doing. That only goes in the...
Yes, I'm going to show that, I think,
next
on the
one?
next slide.
Okay.
Yeah. No, okay, so this is first, because I don't really see what's going on. So this is the residuals of the Greiser and Kalka model. It has a different magnitude scaling compared to the mixture model. So just compared to the average model. And it also has different distance scaling compared to the average model. I mean, this is not necessarily a bad thing. If a model is far away, it's just far away. It doesn't say anything about quality or anything. It just says it's far away. So we still need to understand why it's far away. And so this is the, okay, we should skip that because this is the Bindi model for 3 seconds. Now this weird magnitude scaling there actually disappears. Okay. So this is now the NGA uncertainty model of Alatic and Young's. So what this is, so this is the uncertainty in the median predictions is a function of magnitude and period. So it's basically a constant for magnitudes until, I think, 7. And then it increases linearly with the magnitude. And it's also constant for periods until 1 second. And then I think it also increases linearly with, well, for long periods. Right? With the log period, okay, sorry. Right. And okay, so this is developed for the peer report versions, so not for the earthquake spectral versions, but I just put them in there anyways. So what we see, these gray points are each now the NGA 13 models, plus and minus 1 sigma. And what we see is that they actually, so this is the Buert al-13, this is the Abramson al-13, Campbell, Bosogna, Chow and Youngs, and Idris. And so they all follow basically the same directions. So that means we're shifting them up and down, but we're not shifting them in any other direction. The reason being is that these are all, that this is the pointwise uncertainty, and we're not, so basically every prediction in the median would have this uncertainty, but if we're making joint predictions for everything, we should take care of the joint uncertainty of all predictions, which is not included here. Okay. I hope that made a little bit sense what I said. The same thing is plotted here for 1 second. Basically follows the same trend.
If I try to
Yes,
restate
sure.
what I
Right.
think you said, here we've just got uncertainty in the constant term,
Yes.
and you want all the joint distributions of
Well,
the uncertainty.
basically, you should have uncertainty. Well, you should also have uncertainty in your scaling.
Correct. So all of the
yes.
coefficients
Right.
and their correlations. right,
Exactly.
being tracked.
I'm going to show this next,
Okay.
actually. Well, not for the NGA models, but for something else. Okay, so this is the reason why I included this European dataset model, so this is, well, it's not anything publishable, but this is a simple model that I learned, that I created on this dataset that Sinan was talking about. And so what I did is I calculated a Bayesian ground motion model there, which allows me to keep track of the uncertainty of all the parameters. So this means I have a joint posterior distribution of the parameters. And what I then did is I sampled from this joint distribution. And then I actually sampled 1,000 times. And then with each of these parameter combinations, I predicted medians. So basically for the same thing, so magnitude 5 to 8 and distances 1 to 10 kilometers. And what we see here is then the epistemic uncertainty in the median predictions.
You still use the Akar functional phone, right?
No, this is a slightly,
You need to use the microphone, but I will restate it for you, Christine.
Yes.
Question, are you still using
No,
Akbar's form?
The reference is to the database paper.
It's a fully statistical model.
Yes, so it's a similar form, but this is slightly, it's a simplified form. So this is also why, I mean, here you have, in the edge, you have some kind of oversaturation there, but, so basically all of these are median predictions based on parameter combinations drawn from the posterior distribution of the parameters. And when I plot them all, it looks like this. So in this case, I really have a whole like circle around the mean, the median, the mean of the U of this model is here, which means I really accommodate, so the epistemic uncertainty accommodates differences in magnitude scaling, distance scaling, and up and down scaling. Keep in mind, so this is PCA, principal component analysis, so the simplest method, but the point is these are 1,000 points plus the 14 GMPEs, and there's no way I can do this with the other methods. So this is just way too much data. I would just take way too long.
Are we allowed to ask questions?
Probably
Yes, but you have to use a microphone.
Yeah, just for clarification, you said these are a posterior distribution of the parameters. So,
Yes.
and the likelihood you derive from the data set, from the European data set, where did the prior come from?
Yeah, so this is also why this is not publishable. So the prior, I used a very, very broad prior over the parameters, which is not really what you should normally do, but I didn't want to spend overly too much time on this thing
Okay.
there.
Thanks.
So this is something similar. This is what Brian showed it. This is the GMPE space for the NGA West 2 models. And so what he did, and correct me if I'm wrong, he fitted predictions of the NGA, of all the 5 NGA West 2 models to the same functional form using mixed effects regression and using the GMPE modeling groups as the group factor. So instead of using earthquakes as the group factor, having the different modeling groups as group factors, they are all fitted to the same functional form, also for vertically strike slip and VS3760. And then he gave me the mean parameter estimates and the covariance of the parameters. And this allows, and then I again sampled 1,000 parameter combinations from this multivariate normal distribution of all the parameters and made predictions. So so this is then the prediction. The gray lines are all the predictions. The blue lines are the different NGA West 2 models. The same here, and in red, which is somewhere in there, is then when I use the mean parameter values directly. So, and again, you see now with this joint distribution, we end up covering the whole space. We actually end up covering more than everything else because this is a normal distribution, and when I sample 1,000 times, I tend to also sample the tails of the distribution. All right, this is that one. And now, so what we did so far is we have magnitudes 5 to 8, distances 1 to 200, and each point is equally important. But this is, of course, not what we want for the hazard. So I calculated something which is, well, similar to hazard. I call this the poor man's hazard. So here I have probability distribution for the magnitudes. I have a probability distribution for distances, which is based on Mülheim-Kellich in Germany. And then I have for each of my, so this is continuous, and this is then the discretized version. And then I weigh each ground motion value in this long vector that I have by its probability of the magnitude and the probability of the distance. And then I visualize those vectors instead of the real ground motion value vectors. And there was something seriously wrong what I did last. So this is based on an older plot, but this is correct. So this is, keep in mind, this is PCA. So here, this is using the PGA values. And this is using the hazard values. And what we see is that the picture changes changes a little bit from here to there. So, for example, basically the Bindi model is now somewhere in there, which is actually down there now. The reason being is that we're basically taking out large magnitudes.
Right now, emphasizing the smaller magnitudes here.
Yes, so right now we're emphasizing small magnitudes and distances between 10 and 30 kilometers.
But we could have used weights based on the
Yes,
deaggregation,
we
right?
could use you could use weights based on any something
Right.
else. Yes. So I just needed to have some sort of reference there. Okay. Yes.
Norm answered my question.
Yeah. Right.
Oh, Norm asked the question I wanted to ask.
Okay. And that's basically
Okay,
it.
so can we go
yes.
back a couple?
Sure.
I think there's going to be a lot of questions, but let's start with this one.
Yes.
So this plot on the left gives us a way of saying these are all the allowable solutions, right? Or that are consistent with the NGA models
yes.
with correlation, parameter variability to that. So our models, if we've got a hole there, I could identify a point, let's say up near the top, and would we be able to tell me what that model is so I could now
Yes.
use it?
Yes. I could actually go there and look at the, well, okay, in principle, I could
Recover the model.
recover the parameter combination of that.
And so we
particular
could
model.
create that GMPE.
Yes.
Okay.
Yes. Yes.
So just to follow up on Norm's comment, when you pick up a model that's near when you see
The
a
center?
gap, yeah,
Yes.
you can't. I think it's not appropriate just use it because that model may be sampled with a low or a higher probability than the other one. So that what I'm trying to say, that a dot, you put it there, could represent a say a curve that's on the right that's on the upper tail. Okay, so if you look at all those dots as a histogram, okay, right? So most of your when you're at a locate an area where the probability mass function is high, you have more. You have. So we need to find out whether, okay, there's what I'm trying to say is some points. I'm hoping that some of the points here are actually sampling from the
tails.
From the
Yes.
tails.
Yes.
Okay. So so when you want to add another GMPE to your logic trees, you need to find out not just find out which GMPE it is. You also need to find out what is the probability.
But this is only relevant if you think that this is where you want to end up. So, I mean, it might be that the ground motion model that you're trying to capture is actually up here, which is probably not correct, but it might be. You know what I mean?
But those get down to weights
Yes.
on the models, and part of it is
Yeah.
saying, do we have a set of candidate models that capture the range that we need
Yes.
to get? And if you would look at this and say, let's say the procedure is working in this example, I've got all those colored points, but they're not sampling as broad a range as the gray
No.
point. So
No,
it looks
that's right.
like we're
Yes.
missing something, and it would help to know whether that direction was magnitude or distance
Yeah,
or
sure.
scaling
Right.
again. But it looks like we're sort of stretched out in the left to right, along the x-axis more than
the
up and
problem
down.
is, I mean, this is really
PCA.
this PCA, so it's not really recovering all the directions. So it's because it's flat, you will end up with two directions actually the same thing.
Okay.
So
And the other models will take too long
Yes.
to run,
Yeah.
is the basic problem.
So I can maybe run this. Well, this is 1,000 points. I can probably run this with, I don't know, 50 points or something. Well,
But let's not worry about computer time.
Okay,
You're
right.
at a place, that's a solvable problem.
Yeah.
Okay. So on your PC, it would take too long, but there may be other ways to
Yes.
take it.
I have another suggestion is, now you're forming a prediction, right? So you have a large, huge dimensional vector
right.
that you need to map. But if you just reduce that by just considering the coefficient, okay. Now
Yeah.
this is a 10 parameter model, so you have dimension of 10,
Yes.
then you can map it much easier.
We tried that a long time ago, and we ran into some problems. I don't remember which ones, but I can try that. I can try that again, yes.
Okay.
So. The thing is also, so the point is, so what I also did, I tried to look at the parameter combinations, but the problem is, because they trade off so much, it's not that you have, like, the values of one parameter is low here and large there.
Right.
So this is the prediction. So this is not the parameters. So basically, because they trade off, you might have this, like C1 has one value here and the same value here, but just the other parameters are different. But they give rise to the same predictions, or very different. Yes. Okay. We have some.
Doug Drager. So the question I have right now is, in computing the grade points, how would that distribution change, and how would the tails change if you just remove one model from that set, from the NGA West model? But the other important question is, what if there was an additional model that we don't have? How would that change? So, for example, the hole that Norm pointed out, where we might want to interpolate to develop a new model, how would that change if we had different information going in? Or is there a way that we could assess that?
I don't know at the moment. But the point is, I think if we remove one model from the calculation of these things, but if we then still sample from the full distribution, I think we would get the same picture. We would get the same range of well, a slightly different range probably, but we would get overall the same range of predictions.
Because these points aren't a linear combination of the other ones,
No.
right? This is now
Right.
extrapolating out the tails of the
Exactly.
distribution. So it is creating other models. I think the question is, are we creating models that are not realizable or have
Sure,
some
right.
physical problems to them? And that's probably the other, some constraints have to be thrown on these things at the end. Bob,
How do
yeah.
you set the constraints?
Well, you could say the distance scaling can't go back up or something
Yes.
like that. You could put monotonic constraints on a lot of the different parameters? I'm not quite sure.
Question, well,
If we go back to your back whole plot to the salmons map,
This one.
no, back where you had the self-organizing map. So on this one, supposedly you said you could construct
Well,
predictions in each cell.
Yes.
So each cell,
Each
cell has a set of predictions for
Yes.
all the.
Yes.
So conceptually, we could fit a GMPE
Yes.
to those cells to
Right.
create a model for every cell on that map.
Exactly. You could do that. Yes.
And then we could look at those to see whether they made any sense, at least in our judgmental
Yes.
sense, to see whether if it was a hole, we thought there was a hole here, and we built a model in there, would it make any sense for, would it be a model that if someone had published it, would we use it?
But these points now are linear combinations of the other ones, is
No.
that right? They're not?
No.
They're still separate?
Yes.
Okay.
Right. So yes.
okay, yeah, can you go back to the PCA plot? And actually, this may get, let's see. There.
This one.
Okay, any of them.
Okay.
If I understand it correctly, each point in that plane, you could construct the corresponding GMPE by simply summing the eigenvectors.
Yes. Well, there are two things. So well, if you tell me you want to have a look at this plot,
Yeah.
I could actually go ahead and, well, I could keep track of what I plot and of all the parameter combinations that I plot, and I could go and I could actually take these parameter combinations, these particular parameters, and plot them. But I can also reconstruct a point on that plane by just taking taking that particular location on the plot, and then use the two principal components, the eigenvectors, and reconstruct the ground. So I can basically, for each point here, you can reconstruct a ground motion model.
Yeah, that might be a useful way
The
to
thing is,
to visualize these things.
the problem is, of course, that I think in this case we're at we're explaining maybe 80% of the total variance with the first two eigenvalues.
Yeah, the
So-
rest you can manage some other way as,
Yeah,
another uncertainty that is kind
But so there are two ways. So if you tell me I want to have a look at this point, I could recover the parameter values, or I could reconstruct predictions on this using this particular location.
But you cannot do it with the other one. As Bob
Well,
was asking.
for this self-organizing maps, I can use each of these cells as a prediction.
Okay.
Um,
Okay, nice.
So last question, then we're going to go on to Bob. Just go on.
All right.
This is to make sure I understand, but I think you can illustrate the point as well. You get 80% of the variance because you're only using two principal components.
Yes,
essentially.
but
Now-
yeah.
Now, an important question will be if what is relevant for hazard at the site is only a small subset of all the data, isn't that part of the variance precisely what's missing here? Because this is controlled by magnitude and distance
Yes.
scaling over a wide range of data. So in other words, one of the direction in which the relevant data for hazard is may not be captured by one of those two principal components that you're using.
Very quick. So that could be resolved by using a weight related to the aggregation.
Right.
Okay. So there's another idea is that the plots on the right are actually
Yes.
an estimates of the range
Yeah.
of the prediction based on 1,000 random samples of GMPE from the space. So if you want to obtain an estimate of what is the epistemic uncertainty due to model variability, The plus on the right actually give you an estimate or based on the available 5 NGA models.
I mean, you could also repeat, of course, this exercise using all the, well, 8 models or using more models, and you have some more information in there.
Okay,
So.
thank you, Nico. The thing to take away from this is we're trying some new methods. We're trying some new methods to see, have we captured the range, right? And then as well as part of the distribution would be the weights that we start to associate with that. So Bob is going to now try to start to address this in a more traditional way of how we captured the range, but I think that the tools Nico has just showed us is going to be another way to sort of push the bounds of those approaches.